introduce this item. This is a follow-up being brought to the board at the request of getting more information related to contaminants of emerging concern, specifically with potable reuse projects and also in comparison to other traditional water sources such as surface water and groundwater. So Andy Salveson is one of the project engineers working on the groundwater replenishment feasibility study, and he has a lot of background and experience with CEC, so we asked Carollo to develop a technical memo, which is in the board packet. I just want to do a quick introduction about Andy. He does have 19 years of experience in the environmental and civil engineering field. He is a graduate of UC Davis, and a lot of his graduate studies did focus on the research of CECs. He's been working on over $4 million worth of projects related to the studies and evaluation of potable reuse projects, and has been doing a lot of initial work on CECs and permitting with respect to projects such as Santa Clara Valley Water District, Oxnard, Big Springs, Texas, the City of Los Angeles. He is working as an expert panel on the National Water Research Institute and also the World Health Organization studies. So with that, Andy is here. He has several slides that are going to walk through the information that is in the technical memo, and I'm going to turn it over to Andy.
All right, thank you. Good evening. I really appreciate all of your stamina. You look a lot more energetic than I was feeling back there, although the rate study was very engaging.
You managed to stay awake.
There is a clicker.
Oh, that's here. So you're probably wondering, what are these big things here, right?
It's the rate study, isn't it?
No. This is, so, hold on. So what we have is volume 1, volume 2,
Let me get
volume 3 of the literature review.
Mm-hmm.
And these, we have 2 copies of these, and this is actually half of the literature that has gone into the document that I'm going to be summarizing in 15 minutes. So it's quite a task to actually put it into 20 minutes or 15 minutes of slides. But these are for your staff and whoever wants to use them. And again, this is half of the information. We picked out the stuff we thought was most relevant. If you want the other half, we can get those for you. There was a bit of guilt going around the office as we were photocopying that many pages. So just take a quick moment, give you a little bit of my perspective. In 1993, I was a graduate student at UC Davis, and at that time I was looking for a research project. And I was reading about things happening at the University of Florida, and there was some problems with alligators and reproductive effects happening out at Lake Apopka. And I picked that up, and I created from that the first examination of CECs, hormones, pharmaceuticals in our water supplies in California. Since that time, going through 1998, where I started potable water reuse, working with David Sedlak at UC Berkeley. His first work was with me looking at hormones and pharmaceuticals in potable reuse projects at Dublin San Ramon Services District. And then since that time in 2002 is really when all the research started cascading in. Been looking long and hard at CECs, and so when I stand here with confidence in the ability to produce potable water from wastewater, it really comes from original concerns that I had as a young student and continuing to follow up on the issue. So what we're hoping to do here is present you with the information we've gone through, allow you to look at it, digest it, and get back to us with any further concerns so that we can dig into this further for you. So with that, just a quick run around the country on potable water reuse, and of course the focus is California. But properly engineered potable water reuse is supported by national health experts. So this information's in the literature that you'll see. But of course the state of California Division of Drinking Water, formerly California Department of Public Health, they do completely support potable water reuse, and formal regulations were finalized in 2014. You have the National Research Council, which is part of the National Academy of Sciences, and in 2012 they documented the safety of engineered potable reuse systems and the high water quality that can come from those. California Medical Association in 2012 based upon their review of the literature on water quality and potable reuse, they produced a letter supporting non-potable and potable water reuse in California. And then you go outside the state and you find the Texas Commission on Environmental Quality, for example, multiple approved projects based upon a case-by-case analysis, different than California, and you'd expect that. Texas having a very different regulatory approach, but Texas has the country's only currently operating direct potable reuse system, and I have a few slides on that. And then we can tour around the country. Arizona, Virginia, Colorado, New Mexico, they all have different ways to regulate potable reuse, but each of them have come to the same conclusions and the same approach to risk minimization for potable water reuse. So within California, and I'm sure you've heard about some of these projects, Orange County Water District's the big one, but what I'm actually showing here is some of the recharge locations. But you have the groundwater replenishment system for Orange County, Montebello Forebay, that's the Los Angeles County Sanitation Districts, West Basin Municipal Water District, working in partnership with Los Angeles, the Water Replenishment District of Southern California, Inland Empires, and Cambria. And so you had a Cambria visit earlier, so I heard about that tour. So Cambria is the latest one. Those are current groundwater recharge projects for potable water reuse. And then you have near-term projects. Santa Clara Valley Water District by 2020 has big goals. Right now they're not doing any yet. Oxnard, I'm working with them on their permit. City of Los Angeles, we're expanding one of their treatment facilities for potable reuse. Metropolitan Water District has plans to be the largest potable water reuse agency in the country in the next 5 to 10 years. They're looking at 200 million gallons a day of potable reuse. And then in the San Diego area, you have Padre Dam in San Diego. So there's a lot of projects moving forward. So just always good to just highlight the potable reuse slide. I think everyone here understands it, but in case there were people in the audience that didn't have a full understanding, you've got your urban water use cycle. So you've got at the left, you have your water treatment. It goes through the home to a wastewater treatment plant on the top right. As it moves clockwise, advanced water treatment. In this case, we're showing a lake for an environmental buffer, but it's also a groundwater basin. It's extracted, treated to different levels depending on the quality, and then back to the customer. That's your indirect potable reuse process. So in response to concerns from the board, Carollo and engineering staff put together a detailed literature review on CECs, and I should have said CECs. What are they, right? The compounds of emerging concern, that's the common vernacular. It is hormones, pharmaceuticals, personal care products. It's essentially things that aren't currently regulated by EPA, generally falls into the CEC bin. So what you see there is our draft, which we completed just the other day, and we've gone through revisions with engineering to make some changes and update it. And that will be available. I don't know, Melanie, exactly when this will be available to the board, but
This paper?
Yes.
It's in their packet.
It's already, all right.
And it's on the website
Okay.
right now in the packet, but we'll separate it out,
Okay.
Post this meeting and put it on our website.
Okay, so,
And we have read it. And we, yeah.
wow. Amazing. All right. And you still let me speak.
And then we're gonna ask you questions.
All right. So in the appendix of the literature review, and so after I put the presentation together, I thought, well, maybe I could have ordered this differently in the literature review. But one of the things is understanding what does the state of California require you to monitor for potable reuse projects. And so I just copied some of the tables from the appendix of the literature review. It's the standard MCL stuff, inorganics, you have primary MCLs, secondary MCLs, radioactivity, regulated organics, you've got volatiles, semi-volatiles, you've got, then we start moving into things, disinfection byproducts, that is obviously a concern in any water supply. Then we go into notification levels. Now we're starting to get more stringent than drinking water requirements. A large number of pollutants that we look at called in the notification levels. We then look at monitoring trigger levels. This is from the State Water Resources Control Board. And then we have CECs as defined by each regional board. They kind of have put their own stamp on it. And so on the bottom right, I show the CECs that the LA Regional Board is putting into monitoring programs. Yes?
I was noticing in the document, you mentioned that, the non-polar things can be an issue with the reverse osmosis. and those are NDMA, dioxin, and disinfection byproducts. And I do see NDMA up there.
Yes.
I didn't see dioxin in the list.
1,4-dioxane is handled, it is on there somewhere. I think it's an MCL. There's an MCL on 1,4-dioxane.
Okay.
I have to go up to that. And that's absolutely right. And that's how we get, I'll show you the UV advanced oxidation process, which was in the literature review.
Okay.
So that is part of the multiple barrier process. We like to think that reverse osmosis removes everything. It'll remove, I was just looking through this. I shouldn't tell you that, but while one of the previous presentations, I was looking through this. We'll see reverse osmosis remove about 3 log of a lot of these trace pollutants, but some of them do get through, and that's why you've got the added barrier.
Can I ask you a question about that?
Yeah.
I just don't get, and I thought you're the person to ask, with the tiny pore size and not allowing, like, same kind of membrane that you're excluding sodium and chloride,
Right.
how do these, what seems like larger molecules get through?
Right. So that's right. So, well, first is
Because
that
they're
there
not
are small things that will get through that are smaller than the semi-permeable RO membrane. So there are some things that will get through that are very, very small and they're not charged. And so they can find their way through the membrane.
And sodium chloride is charged.
That's what I was wondering, if it was the charge.
And I could get, I'm trying to recall if I put there's a very nice graphic which shows all the different pollutants that we know of and the size of the RO membrane. And so salts start falling into that size of the RO membrane though. So you'll see salts will get removed, but not entirely. So we'll see about 97% removal of salt. So some is getting through, and we use that as actually a monitoring tool for the performance of the system. We expect a certain amount in and a certain amount out, and if that starts changing, then we know that the reverse osmosis membrane needs repair.
Okay.
But yes, reverse osmosis is a wonderful barrier. It is not an entire barrier to itself to purify water. You've got to combine it with other processes.
I got that. I just was curious about why.
Yeah, I can update or provide the graphics that show a picture of these things. So some interesting concerns when people talk about CECs, one of the things they'll say is they're not regulated, and that's right. That's how I defined it at the beginning. If it's regulated, to me it falls under an MCL and you have drinking water requirements to meet. So there are compounds that we have a lot of toxicological data on, but EPA goes through and they update their lists of things to regulate, and they will regulate them if there's a toxicological effect and it's in water at a concentration that is a concern to them. And so what we find is that a lot of things take a long time to get onto their list and for them to evaluate and for them to then take off the list or decide to include as an MCL. What the industry has done, and this is referencing the work from the National Research Council, but this has been done by a number of groups, is they've looked at the CECs and they've done their own health risk analysis. And they've said, what level is there a concern for these to be in water? And what is the margin of safety compared to the water quality? So they'll say, if there's any kind of biological effect, let's set that as the number we want to stay below. And then they'll say, okay, in an MFRO, in a potable water reuse advanced treatment train, how much lower are we below that? And that becomes your margin of safety. And so what you find is you start looking at these CECs and you'll see that ibuprofen at the top has a margin of safety of almost 300 million. Some things, the perfluorinated compounds, that's the PFOA and the PFOS, those are kind of new. They're a new CEC. And what we find is that their margin of safety is acceptable based upon the health experts' review of this, but it's not to the same level. And we do keep searching. That's an important thing. Perfluorinateds came out in the last few years. We look at them. We understand how the treatment is. We look at the health risk of those compounds. We're looking at antibiotic-resistant genes now. And is that an issue through potable water reuse? So we keep looking, and we then say, is our treatment sufficient? And you can see when we look at these CECs, in fact, when the industry's looked at the broad spectrum of CECs, our answer keeps being the same thing, that this water is protective of public health. Now, it's important to highlight that this is not just a potable water reuse issue. This is a water issue. There are CECs in water. Now, it depends where you're getting your water. If you're getting it out of the Mississippi, You're getting it out of the Trinity River in Texas, you might have a little more CECs than if you're getting the water out of the top of the Rocky Mountains. But what you do find is that there are trace pollutants in just about every water that you test at very, very low levels. So I've included in the literature review some examples of that. Some of your own water quality data was provided, and that's included later. But this was some work done at Lake Huron, and you can see, you can't read it all, but you've got a range of CECs on the bottom axis, and you've got the little blue lines, and those little blue lines approach, in this case, 450 nanograms per liter for one of the CECs. And then as you go through treatment, we bring those numbers down. And it's the same thing when we deal with potable water reuse. The CECs are in wastewater, and we bring them down. We bring them below detection. So here is here's an example potable water reuse treatment train. On the left of the diagram, you've got a wastewater treatment facility that would feed a secondary effluent so it's already been treated to a relatively high level, goes through membrane filtration, ultrafiltration, moving left to right, reverse osmosis membranes. We add in an oxidant, in this case either hydrogen peroxide or sodium hypochlorite. That oxidant then carries through a UV or ultraviolet light reactor. You get advanced oxidation through that process, and then that water could be injected into a groundwater basin, later extracted for consumption. Yes?
One of the things I asked the Santa Clara folks when we toured them is why they only do UV and they don't have AOP.
Yes.
And it sounds like that is a requirement from the state, so how do they get away with it?
Yeah, so I'll tell you. So Santa Clara Valley Water District is a good, maybe is it all right if I provide some context?
Sure.
So Santa Clara Valley Water District has an 8 million gallon a day purification center. It has all the processes you see there, but there's no oxidant. That's because it's a non-potable water reuse project. They take that water and they get the salts out and they blend it with other purple pipe water, and then that goes out for irrigation only. As they move to potable reuse, they are going to have to make sure that UV system has enough dose, enough energy, and then they're going to have to add in the oxidant. So they will have to do that.
Okay.
Yep. We've actually done studies with them to explain what level, what type and dose of oxidant they need to do. And that'll all be published very soon.
And speaking of the level of the AOP, the previous slide had 6 different AOPs, and
Yeah.
I was wondering what the difference was.
That's
and
what I
why,
was wondering.
And why AOP 4 seems to be the worst of all of them, because the others seem to be, decreasing, but 4 jumps up from all the others.
Yeah, so I can dig into that. They're different dose values, and so what were those exact dose values? I could pull that up from the literature, but it very likely has to do with how much UV energy are you putting in, and how much oxidant. Yeah, time goes into the calculation. It's all about dose.
Mhm.
So I'd be happy to dig that up if you like. It's probably in one of those binders. So again, back to the CECs. I showed you a little water picture just for some perspective. CECs are consistently found in raw wastewater. No getting around it. You'll find more in Vegas than you will in California, for example, but you will find them. And to a lesser extent, they're in the treated wastewater. So they go through the primary treatment and some of it gets removed. They go through secondary treatment and a lot of removal happens there. You have a lot of biology breaking down the pollutants in the wastewater. But some of them do get through, and I'm showing that here. And I'll just pick a couple out that you may have heard of. DEET, 154 nanograms per liter. Now, nanograms per liter is really small, but you are picking it up. Let's go down further. I'll pick out something else. Sulfamethoxazole, that's an antibiotic. These things are there. As it runs through the first level of treatment, whether that's tertiary treatment through a sand filter or microfiltration, you're not going to get a lot of removal through those processes. Those processes are conditioning the water, they're removing solids, they're removing pathogens, but those processes aren't doing a lot to remove the CECs. So let's look to the next one. Now, reverse osmosis removes salts, organic carbon, and the vast majority of CECs. Now, you notice I'm not saying all, because that's not the case. Time and again, you'll see little bits of things get through reverse osmosis membranes. So if you look at the far right column, that's your RO permeate. Okay, it has not gone through the UV advanced oxidation process. And you can see you get a little bit of caffeine, 1.8 nanograms per liter. You have a little bit of, in this case, sulfamethoxazole, a little bit of TCEP. Now, just to note, this work, I'm showing you work that comes from full-scale systems, pilot scale systems, and laboratory work. This work was done by one of the renowned chemists in our industry, Shane Snyder at the University of Arizona. So the final product water from a potable reuse treatment is equal or higher quality than conventional water supplies. The National Research Council, National Academy of Sciences concluded that, and if you start digging through the literature and you look at the water quality, you can conclude the same thing. Lots of columns here, and I apologize, Melanie did ask me to highlight a few, and I forgot to do that. But let's pick out one that you're going to be familiar with, the Orange County Water District. That is in the middle of the chart. I will try to highlight it if I have a pointer. People can see the pointer on the screen, I hope. Orange County Water District's in the center. And what you can see for the Orange County Water District is for these CECs, they're all below detection. Compare that to a couple other ones. I've got Clean Water Services in Oregon, CECs below detection. West Basin Municipal Water District, all but one CEC below detection. In this case, it was DEET at 1.3 nanograms per liter. I believe the detection limit for DEET is right around 1. Let's see if that's the case. Yes. So it was detected right above the detection limit.
Caffeine's kind of high there too, isn't it?
What's that?
Caffeine.
Caffeine
Does that-
and
16.
and BPA.
That's right. So a couple more there. So these are consistent. You'll find, for the most part, non-detect after the UV AOP process. Orange County Water District tends to have more non-detections than West Basin, for example. That is consistent. And then compare this with some of the water. Melanie provided us some numbers here for the cells well, before and after disinfection, for the Altivo well, before and after disinfection. And so you see we're finding you've got carbamazepine coming up in one of the in both wells. You've got fluoxetine coming up in one of the wells. You've got nonylphenol coming up in one of the wells. Go to the next
In
page.
some cases it actually increases with disinfection.
I know,
Is that
it's like-
expected? I mean, one
Well-
case it goes from non-detect to 2600.
So I have to say, and I didn't look at the original laboratory work, and I want to provide. When you're doing CEC work, laboratory numbers can bounce around. Maybe a little bit of perspective on that. When I send my team out to do sampling for CECs, they are not allowed to wear sunscreen, deodorant, perfume. They're not allowed to breathe on the sample. So in some cases, we'll have duplicate samples, and one of them is different than the other by a reasonable margin. So it depends on the laboratory QC, honestly. Disinfection shouldn't create a rise in a lot of these CECs. It makes disinfection byproducts, but those aren't on the list. You shouldn't have more like ibuprofen because you hit it with chlorine. It shouldn't happen. So there may be some analytical variability happening there. We're operating down at the margins of the instrumentation.
Sure, yeah. I noticed both these wells are in our area 4, which is probably a good one to use because it's not sewered there, so you'd expect some stuff getting into the groundwater. But would we expect something different in the Prisma, which is largely sewered, but
Depends on if there's a gas station nearby.
yeah.
It's a good question. I wouldn't want to speculate, but groundwater isn't as pristine as we think sometimes.
Yeah.
A couple more data points if I hit you with this, and I'll get into some really exciting stuff. Just these are more pollutants here. You see West Basin's got a couple hits on sulfamethoxazole and TCEP. Orange County, nothing. Clean Water Services, nothing. Now you notice Clean Water Services, the detection limits weren't as low. And then we've got a hit on the Altivo well with that's sulfamethoxazole as well.
Sounds like a good system to copy would be the Orange County one, so they have the best results.
Yeah, and I could get into the details of that at some point if you wanted to know. There's differences in the processes, et cetera.
Yep.
But I would say that, and this is important, is that the state of California, the people that run West Basin, Orange County, they believe that, and I agree with them, that that water is protective of public health. You do see differences in water quality, though. So I want to take a jump to Texas, and everyone always tells me, Andy, that's Texas, but give them some credit. They have done a lot of work to progress the water reuse industry and to look closely at potable water reuse. The Big Spring facility that's owned by the Colorado River Municipal Water District is the nation's only current operating direct potable system. That means there's no groundwater basin, there's no surface water reservoir. Drought required them to move quickly into direct potable reuse. This facility, my team is out there. We're actually just finishing up doing a public health analysis of the Big Spring facility. Our job working for the Texas Water Development Board was to demonstrate if it was producing water that was safe and protective. So we use a lot of tools to do it. I'm going to use some fancy graphics that are kind of neat looking. These are more like a fingerprint. So on the top left is the effluent from their secondary effluent. On the top right is that same effluent. This is the fluorescence graph. Does the water fluoresce? It has to do with the amount of organic carbon in the water. And the top right is the RO permeate. We see no fluorescence. On the bottom is their raw water supply, Moss Creek. And so you can see that the organic carbon, the stuff in the water that we're not defining, it looks pretty similar between a secondary effluent and a conventional raw water supply. So let's look at some of the CECs. This is more data, but it helps provide perspective. The red is secondary effluent, the yellow is microfiltration filtrate, and the green is RO permeate. And so when you start looking through this, you see that the microfiltration, again, isn't doing anything for CEC removal, but the RO is, and you get a few detects. Same story. RO has some things that pass, but a lot removal. So sucralose, we all know what that is. We're getting over 99% removal through RO, but there's a little bit left. There's meprobamate, there's triclocarban that's coming in the RO permeate, but the RO is doing a very good job. Let's add in now the finished water in blue and the detection limit in white. So you see sucralose is coming in right above the detection limit. The finished water has now this UV oxidation process going on to further polish the water. I'm going to remove some things here to make it simpler, and I'm going to show you two things. Blue is Moss Creek Lake. Dark blue, light blue is the finished water from their purification facility. And so what you find is that their raw water has more CECs than their purified water that started out as wastewater. The story is the same when we start looking at other things. Nitrosamines, that's a new disinfection byproduct. NDMA is one of those. You see NDMA in the finished water and in Moss Creek that are very similar. You see no estrogens in the finished water, but Moss Creek Lake has estrone at 0.25 nanograms per liter. See where the analytics are going. You see Moss Creek having more perfluorinated compounds, none detectable in the finished water, but lots in the raw water. So I'm going to conclude. Properly engineered potable water reuse systems produce a high quality water that's protective of public health. Past, current, and ongoing studies continue to look, and then I say look again, at the safety of our water supplies. We are not standing pat. We continue to search for new solutions and to be sure that we are doing the right thing by the public. As new concerns are raised, the engineering community works to understand and address those concerns. You see that in the Water Reuse Research Foundation. You see that in the National Research Council. You see that in the American Water Works Association's Research Foundation. The Division of Drinking Water, formerly CDPH, is dedicated to the protection of water quality. DDW, Division of Drinking Water regulations, are designed to protect public health and do so with orders of magnitude of safety barriers. So with that, a couple of photos of me drinking recently purified water. On the right, I'm at Orange County Water District. On the left, I'm at the City of Ventura at their Pure Water demonstration facility, and I thank you for listening.
Questions, folks?
Let's see, I think I'm good.
See if I got some. I think I do.
Well, I have a general question, and that was, I went to that talk that you were at Berkeley, And some of the papers seem to be devoted to not over-engineering a purification system. And I thought, what are the costs, what are they talking about exactly?
Okay, so you mean over-engineering in terms of treatment processes or costs?
Exactly, yeah.
So I'm going to answer your question. There was a really interesting study, though, that just came out from the Australian Centre of Excellence. They're kind of the parallel of our National Academy of Sciences in Australia. And they said that the safest way to protect water quality is not through over-engineering and multiple barrier after barrier. You have to have some, but it's on monitoring systems. And they found that that is the key to end water quality, is effective and redundant monitoring systems, online devices. So that's where we're, as an industry, we're looking to couple that. So you have multiple barriers. You provide the ability to reduce a wide range of pollutants through several processes. So if you look at the potable reuse treatment train that I mentioned, we handle pathogens through 3 different barriers. And then we have an element of time also in the groundwater that provides another barrier. If we look at trace pollutants, we handle those with 2 primary barriers, but it's 2 robust barriers, the reverse osmosis and the UV advanced oxidation. So the state of California is very strict on maintaining those barriers. And what we're trying to do is add better and more advanced monitoring and redundant monitoring systems onto them to provide water quality. Outside of California, the industry is looking to do things for less cost, because reverse osmosis is very expensive. It produces an RO concentrate. You have to do something with that. So a high energy, high waste product that needs to be properly handled. And so you see utilities across the eastern U.S. where they have been recycling wastewater as a water supply for 100+ years. That you see them have a little bit different approach, where they say, look, we've been doing this all along. We're gonna do it a little simpler than California. But out here, the Division of Drinking Water remains, and for good reason, remains very stringent.
Rick?
Yes, I read somewhere in here that, I think it was the EPA, in terms of monitoring, lets the monitoring of just 5 CECs somehow be a proxy for unneeded monitoring of many other CECs. How do they justify that?
So there's several reports, and some of them are in the literature, and I'll give you, I have a partial answer for you. I'd have to go back and look through it in detail. But the surrogates, and I believe the ones that are, there's 2 different groups. You have the LA Regional Board that I presented in the memo, and then you have the State Water Resources Control Board Expert Panel. And the State Water Resources Control Board Expert Panel said, these are the things that typically get through an RO membrane because of their size and their polarity. And these are the things that should be removed through an RO membrane. And so they pick some that represent a broader class. So it's a good surrogate. You remove this, you should be removing all of that. And some things aren't going to get removed, and then you've got to look for them in the subsequent process. So what you end up with is if you are monitoring for certain pollutants in the RO that should be removed by RO, and one of those comes through, now you know that you possibly have a larger issue to deal with. And then on the UV advanced oxidation process, they take specifically ones that get through. So they say that let's pick 2. NDMA is a disinfection byproduct, and you are required to get that down to a very low level, below the notification level. And now, and this is new with the latest regulations, you're required to continuously demonstrate online that you're doing that with other surrogates. So we're looking at some with the Santa Clara Valley Water District, they're really pioneering, looking at some new surrogates so that you always know that NDMA is where it needs to be. So that's one, and then the other is the 1,4-dioxane, which is an organic. It's different than the NDMA. 1,4-dioxane is an organic, and we know that if we destroy 1,4-dioxane, that we're destroying a much broader group of trace pollutants that could possibly get through reverse osmosis. And then same as NDMA, we're developing those surrogates so that we know that if we do this one simple thing, for example, like if we destroy chlorine residual, which there's a chlorine residual hitting these reactors. If we destroy chlorine residual, we actually know that we're destroying a lot of any other trace pollutant that's coming through. So developing that level of confidence. So these expert panels have looked at that, and they've tried to say, one thing represents a broader class. Now, the LA Regional Board has come back and said, yeah, that's great, but we want you to sample more. And that was really just an added conservatism. When you go back to the experts on the state board panel, they'll say that wasn't based on science, that was based upon just concern about CECs, and we want to see more data. And you can understand that perspective, and so the agencies move forward and they do that work.
When these surrogates are chosen based upon theory or general principles, do they then go back and test that they really do correlate just like they had predicted?
Yeah, there's a lot of work that's been done. So they base the correlations on past work. And then the state board, the expert panel, comes back every few years and meets and revises their policies. So the CEC panel that is later this month, I'm actually speaking on it, on the use of surrogates for CEC removal. They are going to take the information they gain from that, and depending on what they hear, they may reconvene the panel and rewrite it. It is intended to be something that's updated every few years as the industry learns. So.
I had one question. What we've been talking about mainly is looking at what comes out the back end of the facility in terms of, its quality. But of course, for the indirect, it then goes into the ground, or in some cases a reservoir, and then comes out. And I know for the Orange County facility, the problem they had was that one of these constituents got created in the ground. They were using chlorine, I think, as the disinfectant back then. And chlorine into the ground was actually creating NDMA. And that was enough of a red flag that they knew that that was something they created. But if you just take the purified effluent and put it into the ground and test it when it comes back out, you're testing not just it, but all the other stuff that's in the ground. And
Yep.
so
Yep.
how do you know that those kind of things haven't happened?
All right. So start with the basic principles of disinfection byproducts, and it's an exchange.
Mm-hmm.
So in water, we have, the advent of chlorination in our water supplies and in disinfecting our wastewater has had a hugely beneficial impact on public health.
Mm-hmm.
But we make disinfection byproducts, and those disinfection byproducts are probably the most problematic of the things you find in your water, the things that we made. Trihalomethanes, haloacetic acids. And you're right that NDMA was being formed in some of the purification processes. They wanted the chlorine to stop biofouling of the membranes. They wanted the chlorine to provide disinfection.
Right.
And wham, you
Stop using it now.
got hit by something else. The last one that's doing this is City of Los Angeles Terminal Island, and we're working with them to convert them from chlorine to a UV advanced oxidation process. So it takes time to implement these changes, but everyone's going that way. And so a fair question is, what else are we making that we haven't measured?
Exactly.
Fair question.
Mhm.
And we keep sampling and we keep looking. And in these groundwater recharge projects, we test the water as it's going out.
Mhm.
We have these surrogates that tell us if we're doing what we're supposed to be doing.
Right.
And so hence, by measuring a surrogate, it's the whole quality assurance approach. If this works, that works, and the third thing works, then you know that water quality is good. But then we test it as well. Goes in the ground, you have monitoring wells that are well spaced before you have your extraction wells. And so the monitoring wells are tested and the extraction wells are tested. So if you're having things changing because of unintentional, good intentions have an unintentional consequence, we would be picking them up if we're sampling for the right things. Now, when we're looking at disinfection byproducts, we've got good analytical methods. We can tell if we're under an MCL. So it comes back to the CECs. What are we making? How can we tell what we're making when we're looking at very, very low sub-nanogram per liter organic carbon, and is that a health risk? And the industry's belief is that these low levels, again, sub-nanogram per liter, even when combined into one concern, are well below the health levels, and that is somewhat evident by some of the discussions on the safety levels that I showed earlier, whether it's 80 or 300 million orders of safety differences. So I guess that the only thing I would say is that we do continue to look. There's new research into disinfection byproducts from UV advanced oxidation processes. A lot of that work was done by my graduate student that worked on this at Colorado Boulder. Young PhD, I should bring her next time, Asta Parker. That was her whole PhD research, was looking at advanced oxidation byproducts. And the conclusion in her work was, this is not a health concern. Worry about standard disinfection byproducts, worry about larger concentrations of trace pollutants that get through advanced treatment systems, monitor for those, and don't allow that water out the door.
Of course, it's not just disinfection byproducts, like the case of the arsenic being released in the LA facility, I think it was.
Right, so that was, so there was, yeah, you done your homework. So arsenic release had to do with, and where's the hydrometrics? So I'm not a groundwater
mineral
chemist.
content,
Yes,
wasn't it?
Yes.
Yeah, it had to do with the change in the oxidation potential of the groundwater. You have more oxygen in the water. It then released minerals that had arsenic in it. And so Orange County Water District has gone through extensive studies to look at the release of arsenic and does it exceed health levels. And I believe their conclusions, what I've read, is that they've seen it bump up initially and then it comes back down and it hasn't exceeded health levels. I don't know if you've seen something different.
No.
I think they had to add back in like calcium carbonate or something.
That's right.
Calcium and magnesium, I think, were.
They are, so part of their deal is they're trying to stabilize the water with new formulas. So the water, the RO permeate has a TDS of less than 50 milligrams per liter. Orange County Water District is probably 35 milligrams per liter. And there's no minerals in that water other than that small amount. So they're adding in stuff to stabilize the water so that it doesn't have as much water chemistry impacts in the ground.
Corrosive.
So how this is being handled, this is an interesting thing because it's a real concern.
Sure.
So we're working with the city of Oxnard. They have their facilities built and we're permitting their recharge. And the first phase of the project is we're injecting into a well, we're watching it migrate. It's not started yet. We're gonna watch it migrate. If we see arsenic problems, we're pulling the water back out.
Okay.
And so it's not something we'll just like let it go. We're gonna pull that water out, use it for non-potable purposes, go again. Because what's happened in this, all this arsenic work, all the arsenic problems, not all, a lot of them have been in Florida. And what the Floridians have seen is that after time it goes away because you've oxidized your environment and the problem's not there anymore.
Right.
Well, for potable reuse, we're going to essentially create some balloons underground and that water's going to come out and we're going to use it where it's safe until we get that level to where it needs to be.
So it sounds like there's active research going on now in this back-end processes kind of stuff.
Yep.
Okay.
There is.
Okay.
There's a lot of work going on. It's hard to keep
I
track
want
of.
to thank you for what you've given us, because this really,
Good
for
job.
me anyway, answers the questions that people have been asking us, and we had no data on it. So you've given that to us, I think, very admirably. So I
Okay.
appreciate your efforts.
Yeah.
Yes.
Thank you.
Thank you.
Staff had a lot to do with it too, so.
In a